So hopefully by now you have a pretty good idea what we mean when we refer to knowledge of language and what we mean when we refer to a mental grammar, this type of computational system that we're probably pretty sure at this point must be part of this ability of the human mind that enables us to have KOL. And you might have wondered, when I gave you this toy grammar of English, couldn't I have done that in a different way and gotten the same sort of outputs? So in other words, couldn't I have written a different model grammar, but actually accounted for the same grammatical system? And that's really where the idea of extensional equivalence comes into play. Just to explain the term extensional, there are two ways to define a set mathematically. I could either go and list everything that's in that set and then say everything that's not listed is not in the set and everything that is on the list is in the set. That's an extensional definition of the set. I can also define a set intentionally with an S, not with a T. And that's what I've done when I came up with the set of possible English sentences in our very reduced toy grammar. There's a problem with this, seeing as we've seen that there's creativity and infinite embedding. We have to deal with infinitely many sentences and infinite sets I cannot define by listing down every member. If you try and write down every natural number, you will never get done, so you'll never have an extensional list. Nonetheless, we can think about all the possible outputs and compare them even when we intentionally define sets. And that's really where we talk about the extensional equivalence. So if we think about all the members that come out of this intentional system, are they the same for two grammars or are they different? Right? And so we might say that two computational systems are extensionally equivalent if and only if, and this is what the if here, notice with a double F, that's what that means, if and only if, they map the same set of input representations to the exact same set of output representations. Right? So every computational system, which a mental grammar is an instance of, has an input and an output. And so it's important that when I give it the same starting point, if you will, it arrives at the same end point. Right? And so if I get the same set of endpoints for the same starting point, then my two systems, or my two mental grammars, are extensionally equivalent. And you might well have thought earlier, well, yeah, maybe we could have written a different set of rules that would have given us the same input-output mapping as our toy model of English had. In fact, during that video, I told you about one such possibility. So you might remember that the rewrite rule for a noun phrase, NP, said, well, NP can be rewritten as a D in parentheses followed by an N. And I said, well, let's use D in parentheses to mean that's optional. But we could get rid of the idea of optionality and just write that as two rules. Right? We could write one rule that says NP can be replaced by a determiner followed by a noun, and then another rule that says NP is replaced by just a noun by itself. And that would have given us the same output, wouldn't have changed anything in the possible sentences that we've defined over the same inputs, but the grammar would have been slightly different, perhaps. Now, let's turn to the world of stress assignment, just to make that a little bit clearer, and we'll look at a language called Weri, which is a Papuan language spoken in Papua New Guinea. And unlike in English, where stress sometimes can tell you the difference between a noun and a verb, for example, think of increase and increase. Right? If I put the stress on the end of the word, then it's the verb. Right? Happiness increased. Right? And if I make it a noun, the increase of happiness, then the stress is at the start. So actually that contrasts meaning. That's not the case in Weri. In Weri you can predict where the stress is going, just by knowing the sounds and the sort of interrelations that they have in the language, and by knowing some rules. So that's sometimes what we call non-contrastive. Right? It can't make a difference in meaning. So that situation implies that it's not part of the input representation. Right? For a language where I can make a contrast in meaning depending on where I put the stress, do I put it in the first, the second, the third, the fourth syllable, and they all mean something different, well, then I have to memorize that somehow, right? I have to store that as part of the input representation, and it's not derived. But in this case, well, I don't have to. So there must be a system for a Weri speaker that can derive these things. So we might say the phonology of Weri, which is of course also part of the mental grammar of that language, or rather of every speaker of that language, must have a process that maps stressless representations of words to stressed representations of words. And so let's look at a couple of examples. So here we have akune petal and uluamit. Whatever they mean, it's not important to us. We just know these are words in Weri. And so we assume that mentally they are stored without stress. Right? So their mental representation is a sequence perhaps of these sounds. And then the output contains stress. And now note, if you're doing the reading and you come across these examples, they'll be using different symbols for stress. That's kind of an American thing. The problem is that the IPA that you're learning in your phonetics class right now uses the same kind of symbols they're using for stress, for tone. And it actually happens that Weri is a tonal language too. It has a contrast between high and low tone. So it's not really an optimal way of representing that. So I've just gone ahead here and used the symbols that are actually conventionally agreed in the International Phonetic Alphabet to indicate primary and secondary stress. And so if I have this little apostrophe kind looking thing here before a syllable, at the bottom, that means that's a secondary stress, so there's some stress on that syllable. And if I have it at the top, that means that's the primary stress, so the strongest stress in the word. So this might be pronounced simply like akune petal. And the second one here, uluamit. Right? So final stress really here, and there's sort of like intermediate prominent positions on these other syllables. And so we want to account for that, right? So we need to come up with an algorithm, a mental grammar, that a set of rules that gets us from these inputs without the stress to these outputs with the stress contained. And so let's start by entertaining one way that we can do that, which we'll call the grouping algorithm. And so the first rule that we're going to propose here is that we group syllables into pairs. These pairs we call feet, right? So singular foot, plural feet. And we do this from the right edge of the word going towards the left. And just because that might be useful to you, you might not have a good intention about what constitutes a syllable in a language that you've never spoken. I've put little dots here to break up all the syllables. That's just to help you. So we start from back to front and we say, well, okay, we want to group them into pairs that consist of two things, and we start right to left, so tal and pair. We put some braces around to now indicate that these are a group, that these are a foot. And then we do that same with ne and ku, and we get kune as a foot. Oh, and then we only have a single syllable left. Well, we can't make pairs out of single items, so we'll just leave that, right? The rule doesn't apply. With ulamit, the same thing happens, right? We take mit and a, the second two last ones, make a foot amit, and we take the lu and the u, and we make ulu. All right, then the second rule is going to be that we form feet out of any leftover syllables, right? So feet that are not consistent of pairs. And so that in this form here, where we still have a leftover single syllable, we'll just put some parentheses around to indicate, okay, that's also a foot now. Notice for the ulu mit, we don't have to do anything, right? In technical terminology, we might say the rule applies vacuously. You can apply the rule, but it doesn't do anything. The third step in our algorithm is going to be to assign secondary stress to the rightmost syllable in each foot. So we go through each foot. Here we only have one syllable, so that's going to be the rightmost syllable. So we put the secondary stress mark there. Here we have two syllables, ku ne. So ne is the rightmost, so we put a secondary stress there. And then here we have pe tal, and so tal is the rightmost syllable in that foot, and so we put the stress mark there. For ulu mit, the same. Ulu is the first foot, lu is the rightmost, so we put the secondary stress mark before that, and amit, mit is the rightmost, so we put the secondary stress mark before mit. Now we need one more rule to get the primary stress in place, and so we'll say replace the rightmost stress in the word, notice not in a foot, in the word, with a primary stress. So the rightmost secondary stress, or the rightmost stress at all in this word here, currently is on tal. And so we'll just go and replace that with a primary stress. Same here, ulu mit. We have the rightmost stress is here on mit, and so we'll just replace that with a primary stress. And you notice that these outputs here, if you just ignore the parentheses that we've added, are the ones that we wanted. We had a secondary stress on a secondary stress on ne, and a primary stress on tal, and here a secondary stress on lu and a primary stress on mit. Now, a different way that we could account for the same thing, a different kind of grammar that we could come up with, would be one that employs a counting algorithm. So here's the recipe for that. So first, you label each syllable with an index from 1 to n, where n is the number of syllables in the word from right to left. So we start at the right edge. Here I've again indicated the syllables for you. And then onto the right-hand side of each of the syllables, I'm just going to put a little index number just to keep track what the number of that syllable is. And so tal, I give 1, pe is the second syllable, ne is the third, ku is the fourth, and a is the fifth. For ulu mit, mit is the first, a is the second, lu is the third, u is the fourth, and so on. Then I want you to assign secondary stress to each odd-numbered syllable. So here the odd-numbered syllables are 1, 3, and 5. Right? Notice I've put the index to the right, but we put the stress mark to the left. So it might look a little bit confusing. But tal is the first syllable, remember. 1 is odd, so I'm going to give it a secondary stress mark here. Ne is the third syllable, 3 is odd, so I'm going to give it a secondary stress mark, and so on. Do the same with ulu mit, so I get secondary stress on the third and on the first syllable. And now, last step, replace the lowest numbered stress with primary stress. So the lowest numbered stress that I have is on syllable 1. Right? I have one on 3 and one on 5, but 1 is obviously lower, so I'm going to replace that with a primary stress. I'm going to do the same here. Because we're starting from 1, 1 is always the lowest, so we'll just replace that. Okay, so it seems quite obvious that both of these systems are extensionally equivalent. We give them the same input, namely the string of words without any stress, and they produce the same outputs. So they map the same things to the same things, but they're very radically different. It's not just a matter of, saying, oh, this is optional, or saying, well, I just write two separate rules, right? It's a matter of the complete way that we've built this is radically different. So let's briefly return to scientific method. Right? Recall what Richard Feynman said. Well, scientific method works like this. Right? First, you guess. Of course, you want a good guess. Right? A good guess is one that explains something. And then you compute the consequences of that guess very carefully, in a way that's kind of what we've been doing, right, by stepping through these things, and maybe, in an ideal world, we think about some words that these speakers don't know, and then, check whether our guess is correct. But let's assume, that's something we're already happy with. And then you compare it to nature, and if it disagrees, it's wrong. Right? So here we've made two different guesses, quite radically different guesses, about what the mental grammar of Weri speakers might be that allows them to have this input-output mapping. We've computed the consequences. Now let's assume we've checked in with nature by looking at some more data, perhaps doing a kind of WAC test with words that they don't know, and neither of the results disagrees. So we can't really reject one. Then does that mean that both of them are right? We have to ask which of our two guesses has a better chance of actually being a good model of the mental grammar of a speaker or listener of Weri. I mean, that's what we've done last week, right? We compared two things, and then we said, well, okay, one is clearly wrong because the evidence speaks against it, memorization in that case. And so we assume the other theory is the one that we go with. But here we can't do that. So we're forced to either say, well, maybe they have either of them and it doesn't matter, or one of them is correct and the other incorrect, but we have this problem of how can we tell, right? And of course, as I just said, we can ask ourselves, well, should that even matter? And I'm going to try and convince you that it should. So extensional equivalence isn't enough as a goal, right? You might want to say, well, I've given you an explanatory system, right, that gets it right, makes the right predictions about the world. But that's not all we want to do. But that we've made a commitment to studying a speaker here as knowledge of language. So we're interested in what they actually have in their mind, right? We've defined KOL as a property of the human mind. That's a property of human biology ultimately, and therefore has some biologically determined capabilities. If knowledge of language then is a property of the human biology and has biologically determined capabilities, then they will be one way or another, right? That's, even though we can't see it, and it's, if you think about it like a black box that you can't look inside and you can only see what goes in and what goes out at the moment at least, maybe one day we have amazing neuroscientific breakthroughs, it is just as real a physical object and state of the world, right, a state of neurons and things, as anything else. And this type of KOL, right, I've before called the faculty of language. And the faculty of language, so we would assume, is one way and not another way. And ideally, we want to have a good model that doesn't just get the input and the output right, but that actually tells me how does it work in the middle, right? What's actually in that black box? I mean, that's the really big question that we're interested in, right? So we want to know what the human faculty of language really is capable of and what it is not capable of, right? If we think bigger picture. And it may be that it's only capable of the grouping algorithm. And it may also be the case that it's only capable of the counting algorithm. Or it may well be, right, the way nature goes, it may be that it could do both. So how are we to decide? We've gotten no further. I've given you a reason that I think is pretty compelling as to why we should figure out whether both of them are correct or whether just one of them is correct. But we're still struggling to do that. So let's entertain some meta-theoretical considerations. Okay? So here's our problem redescribed more generally. Right? If we want to know whether some larger system is capable of implementing two models or only one of two competing models, how can we find out which is the case? Well, if we assume that it can do both, but each of them would suffice by itself to account for all the data and all the observations that we make, well, we'd never find a way of proving ourselves wrong. Right? even if they don't completely overlap, right? I mean, here we have a case of extensional equivalence, so this is like, sort of like the worst kind of this problem that we can have. But say there are potential observations even, that would be different, potential predictions. We can't test them right now, but in principle they're testable. Well, then if they're complementary in that area, we still can't tell whether it's the one system or the other, because if we assume that both are present, well, one of them is always going to cover it, right? So there's no evidence, as long as one of them at least is right, that could ever prove us wrong. So that's not a good assumption to make. So our best chance to figure out whether just one of them is true or whether both of them exist in parallel is to assume that one of the models is in fact wrong and the other one is the only one that can, in this case, be mentally implemented. And then if we find evidence that neither of them by itself is sufficient to account for the data, right? No matter how hard we try and how good we make our model and how many twists we make, we cannot unify them, then we'll kind of very reluctantly perhaps assume that both of them kind of exist independently. There's a good parallel in physics, actually, right? The biggest problem, the problem per se in physics for a long time has been that, well, for everything that's happening on a small scale, quantum mechanics is the best explanatory theory that we have. It's clear. And on the large scale, general relativity is the best theory that we have, right? For the large scale interactions between things, gravity and so on, distortion of space and what have you. But the two have some assumptions that are incompatible and they can't really be reconciled. And you can't come up with a good system that's consistent with all the evidence out of quantum mechanics that gives you that, and you can't go the other way around. So neither theory at the moment, it looks like, can be expanded to include the other. So we kind of have to use both at the same time. And of course, what everyone's hoping for, the massive breakthroughs, what people call the grand unified theory in physics, that would be a theory that unifies gravitational theory and quantum mechanics in a single model that has consistent assumptions internally. And that's also a consideration that on a very small, perhaps much less important level we have here. But when we do that, we have to be careful, right? Precisely because of this possibility that maybe there could be a single unified model, right? So if it were possible to find a grand unified theory of Weri stress, well, then the question of having two goes kind of out the window, right? So maybe it's just that our model is not good enough and that there's some truth that we haven't discovered that would help us in coming up with a single system, and we don't need the two anyways. So there are lots of issues that you face when you have to decide things like this. If the evidence that you get by checking with nature after you compute the consequences doesn't give you a deciding appeal. So what do people do when they're struggling in this situation? Well, first of all, right, what I've just argued for here is you will assume that only one of the models is correct, especially if they're extensionally equivalent. Right? A lot of the time you already do that when they're quite close to being extensionally equivalent. Right? And you say, well, usually one model struggles in one area where another is a little better, and vice versa. That's mostly the case that you find. And so you could argue for and against each model depending on how important you think this phenomenon or that phenomenon is. But ultimately, one of them has to be right and one has to be wrong. And then the one that's right has to be fixed, right, and improved to be able to account for the stuff that we're struggling with before. All right, so anyhow, how do we have a chance of discerning these things? Well, there are lots of things that people actually do. So you can appeal to the idea of plausibility. So when a cognitive scientist wants to choose between two extensionally equivalent or nearly extensionally equivalent models, or perhaps they're trying to come up with a new model in the first place, they often ask themselves whether, given everything else that we know about cognition, about the mind, about the biologically determined part, right, including neurology and other biological factors, factors around in the world, and so on, one of those models seems more plausible or more likely than the others, right? Perhaps because it's more consistent with all these other facts that we know about. And we've already seen in our toy model of the English speaker hearer's syntax that they use grouping, right? Counting there is not a viable alternative. I mean, you can sit down, probably it might take you 5 minutes, it might take you 2 hours, but you can very easily convince yourself that it's completely futile to come up with something that gives you infinite embedding and creativity over these inputs of equivalence classes that produces the same type of grammar. So, well, if that kind of grouping, right, and rewriting things, so like, saying, a sentence consists of another unit we've called an NP, and the unit we've called a VP, and an NP consists of a determiner and an NP and a noun, right? You see that that's kind of really replacing things with groups of other things, right? You always get groups, and then you can replace part of that group with another group, and so on. So grouping is really what's underlying a lot of syntactic processing. And then we can say that mental processes generally seem to rely on grouping and categorization a lot. So if you think about how you create meaning out of the world, if I show you a couple of things that are fairly random, but somehow I contrast them to another set of random things, and your brain will straight away go, okay, here's some property they have in common, and here's some property those have in common, right? And your brain really likes to categorize things. Something that it does a lot. In visual perception, things get grouped and categorized. That's why you have the example in the textbook with the triangles. And on the other hand, there is very little to no evidence that this kind of subconscious processes, right? So not conscious doing of mathematics, rely on any type of sort of positional counting. In fact, our brain and our mind seem to be really, really bad at that. Seem to be really bad at keeping track of precise positions and over certain distances. There's a good saying that one used to hear many, many moons ago in many linguistics and cognitive science departments, and that's the brain counts to 2. Right? So it pairs things up, it groups them. Basically, it's like counting to 2. And then it makes a new group if it needs something that has 4 things in it that will put them into 2s, and then I'll put those 2s as groups into 2s again. And then you have a group of 4. And that seems to be a really strong bias in most cognitive systems. So we might thus argue that the psychological plausibility of the grouping algorithm is better than that of the counting algorithm. Right? Given everything else that we know about human cognition, it's much more plausible that they use grouping than it is that they use linear position counting. So that might be one argument one might make to say, well, if I'm going to assume that one of them is right and one is wrong, because that's something I have to do in order to be able to step forward and show whether that really is the case, then I'm going to choose the grouping algorithm because of psychological plausibility. Another argument that people often make is parsimony. You might know this as Occam's razor. It's kind of attributed to an English monk that lived many a moon ago, wrote lots of great philosophical treatises, but who may have employed this principle but never really explicitly defined it. Nonetheless, it's named after him. A lot of time, but really the technical term for this is parsimony. And that's the term you'll encounter a lot when you do linguistics. So given that we have 2 possible explanations, maybe we could say, well, one of them is less complex, makes fewer assumptions, and the other one makes a lot more assumptions and is more convoluted in a way. And so basically what parsimony says is that in those situations it's usually better to choose the simpler model, or in other words, the more parsimonious model. And there are many reasons why we might want to follow that guideline. So we can always add pointless stuff to our grammar. As long as it doesn't affect the output, it's going to be extensionally equivalent. So I could take my toy grammar from before and say you can replace an NP by an NP. I could also say you can replace an NP by a determiner followed by a noun. You can replace an NP by an optional determiner followed by a noun. You can replace an NP by just a noun. You can replace an NP by, let's introduce something new, by an X followed by a noun, and then you can replace the X by a D. Right? I could make all those convoluted things, and they would make my my mental grammar or my model a lot more complex, but they don't add anything. Right? There's no point to them. And so why should I add them? Right? I'm just making my model more complicated, and that makes it harder to also think about the predictions. Right? So simpler models make it, a lot of the time, if they're well defined, easier to compute the consequences and therefore use scientific method in trying to prove that they're wrong. Another consideration that's quite important is especially concerned with assumptions. Right? So if I make fewer assumptions, and assumptions we base perhaps on another theory that we have, or on some other guess, and so assumptions might turn out to be wrong. Right? And so the fewer assumptions we have that we need to rely on, well, the less problematic it is if one of those assumptions should turn out wrong. Right? If I have 20 assumptions that are essentially guesses and theories in their own right, then the chance that one of them will be wrong and that it will have bad consequences and make my own theory crumble is a lot higher than if my theory only makes 3 assumptions. Right? Therefore, my chance of actually being on the right track is usually better in a theory where I only have 3 assumptions than one where I have 10 or 20 or 50 or 100. Remember that the quality of assumptions also matters. Right? It's not just a matter of counting the number of assumptions I make, but maybe some assumptions are based on really good evidence. Right? And, we've done lots of experiments and the theory is very solid, and we're pretty sure that's correct or nearly correct, an almost law of nature, if you will. And then I could have some wild guess about something, right? So of course, my chance if I have a theory that's based on an assumption that is one wild guess, and I have one that's based on 3 very solid assumptions, I might still want to go with the one with the 3 very solid assumptions. So parsimony applied to the Weri stress system, right? We might say that considered in isolation, the counting algorithm is more parsimonious. Right? It has 1 step fewer, only needed 3 steps. However, actually, when you look at other languages, right, we had this issue, well, the last syllable in even counts, right, that was fine anyways. And then in odd counts, we had this problem where we need to put a secondary stress on there. And so we needed to give that an extra foot in the grouping algorithm. But in some languages, actually, when you have that situation, they don't get a stress. Right? So we need to actually, for those languages, to account for them, we need to add something else to that counting algorithm, and then they both have 4 steps at least. And so if we do that, then neither of them, right, really is much easier in that way. So we add a step to allow for that, and then they're on par. So we can't say that one is more parsimonious than the other, because, and here this is about the assumption, not really about the numbers of steps, but about the assumption that that step exists or is possible. Right? I should make that very clear. And so if we consider that consider the two things in a wider cognitive context, well, we can also say that in terms of the assumptions, we already have to assume that the faculty of language is capable of grouping, right? I told you before that, well, essentially what we've done with the syntax model, that's relying on grouping, right? And so if we have to assume it's also capable of positional counting in addition to grouping, well, then our overall model of the faculty of language becomes less parsimonious, right? So if we can say that stress assignment is based on grouping just like syntax is based on grouping, well, then we need to make one fewer assumptions, namely that, there's a mental capacity for grouping in the faculty of language, rather than make the assumption that there's that capability and then a capability for counting, for positional counting as well. Right? So this would be the argument for parsimony, and actually here it speaks against the counting algorithm once again, once we've worked through it, even though initially, right, if we take a very naive look, it might look the other way around. Some other common appeals that people will make are to economy and to homology. So many cognitive scientists assume that the mind-brain tries to be as efficient as it can be with the resources that it's given. Right? It takes a lot of energy to do a lot of mental processing. At one point, we also thought that storage is really limited. I think in the last decade or so, we've learned that actually the brain can store a lot more information than we thought. But in any case, that all costs resources, right? It costs energy on a cell level. And in general, we know from evolutionary evidence and from general pressures on biology and the external world and so on, that biological systems tend to evolve to be more resource efficient over time. And based on this assumption, we may then appeal to economy, right? And say that a model that requires less computation and or less storage is more economical and therefore more likely to be correct. And an important thing to point out is this and or here is not a matter of it doesn't matter. It's a matter of people really disagree. So some people think that storage is really cheap and computation is really expensive. And other people think that storage is really expensive and computation is really cheap. The latter one is, for example, the position that Chomsky held for a very long time. And then many people take a very balanced view. That's where I find myself personally. When I look at the arguments, I don't really see an argument massively for one or for the other. And the best thing is probably if you can keep both of them down. And then you can make an argument from homology. So if you think of comparing different biological systems and comparing different cognitive processes, which are instantiation, of course, of biologically established systems, not just in humans, also in other animals, by the way, then that sort of comparative study seems to show that a lot of the time when nature is faced, let's say, with the same problem, it comes up with the same solution, even independently. So, for example, if you see how birds fly, right? They have wings, and that's developed out of certain types of bones and so on. And now birds are not mammals, right? And they had a completely different evolutionary path to get to their wings than, for example, bats. Bats are mammals, and in bats, what has happened is the arms become kind of elongated, the shoulders twisted in, and their fingers became really long, and the skin stretched out in between. And essentially, they come up with a structure that, on the outside, is very similar, is homologous to a wing, but nature's gotten there in completely different ways. But it was faced with the same problem. I want to make this thing fly, if you will, right? That would be an advantage for it due to whatever pressures existed at the time. And so it arrived at the same solution. So maybe we can supplant that thinking also into deciding between these types of models. And we can say, well, if I know that a lot of other animals do that and a lot of other cognitive processes do it that way when they have that problem, then in the absence of any other evidence that lets me decide, maybe it seems the most likely if nature has a tendency to solve it that way, then here it will do it also. Now the really important thing, and the note that I'll finish on, is that while these things are really useful to know and think about and keep in your mind as you devise theories, if you are confronted with theories, it's ultimately nature that has the final word. Right? Well, so while while considerations like plausibility, parsimony, economy, and homology are useful guiding principles, right? They help us to sort of like rationalize in the absence of other evidence, and they can help us in choosing and devising models that are more likely to be correct overall. They're just a heuristic. A heuristic means it's a method of arriving at something that seems more likely, that's more probable, right? And so they're just things that, from the experience of a lot of people doing a lot of science and a lot of philosophy over many years, has seemed to help in guiding them away from those things that are fruitless in pursuit, and guiding them more strongly towards those that are actually that actually have a better chance of being on the right track, right? And that's where we have to see it. And such a heuristic can never tell us without a doubt, unequivocally, that one explanation is correct and another one is wrong. Right? No matter, I might say the counting rule, well, everything speaks against it, right? Homology speaks against it, economy speaks against it. It's much more costly, right, to keep track of all the indices and so on than just make groups and forget about it. It's, in terms of the psychological plausibility, right, it's worse off, and so on. There are lots of arguments, but ultimately it could still be the case that counting is the right thing, right, that's what the brain does. So the only thing that can really tell us ultimately is the checking with nature part of the scientific method, right? So we need falsifiability to ultimately decide. So the most important principle to always keep in mind is falsifiability, and looking for that consequence that can go and test and that can tell me whether I'm right or wrong.